So we have found that we can find a point estimate x bar for the population mean, and we can find the margin of error e. And once we know the point estimate and the margin of error, then our confidence interval is going to be x bar minus e to x bar plus e. This is the same way that it worked when we were dealing with proportions. We had a point estimate of p hat, we had a margin of error e, and so we found p hat minus e to p hat plus e, and that gave us the confidence interval. But when we were dealing with proportions, we mentioned that the trouble is when we do this way, we have no control on what the margin of error might be. Well, the same is true when we're finding an estimate for the population mean and dealing with the confidence interval. If we just find our point estimate and then the margin of error, our margin of error could be huge. We have no control over that. So in real practice, it's not typically done that way. Instead, because our margin of error formula is t sub alpha over 2 times s over the square root of n, as the sample size n increases, the margin of error goes down. So if we choose an appropriate sample size, we can control what the margin of error needs to be. And that's the way it's generally done in practice. So doing the same sort of approach that we took when we were dealing with proportions, if I solve this formula for n, it will give me a sample size that would be needed to be within a given margin of error. So let's do that. Solve our formula for n. So if I'm going to solve this formula for n, the first thing I'm going to do is multiply both sides of the equation by the square root of n. So multiply both sides by the square root of n, and that gives me the square root of n times e equals t sub alpha over 2 times s. Next, I can divide both sides by e. So if I do that, then the square root of n is going to equal t sub alpha over 2 times s divided by e. And finally, I can square both sides. So if I square both sides, that gives me n equals t sub alpha over 2 times s divided by e squared. So again, this is just our margin of error formula solved for n. So I can choose the margin of error and then use this to figure out what the sample size would need to be so that I'll be within that margin of error. Now there's just a couple of issues with this particular formula. One, s. We have to have a preliminary estimate for s. So there has to be a previous study or a preliminary study that's going to give us an idea of what the sample standard deviation is. So for example, we might start with a sample of say like 30 and figure out what the standard deviation for those 30 data values are. We use that as a preliminary estimate to do this calculation so that we can figure out what the real sample size is that's required. If we find out that the real sample size required is say 80, we had a preliminary sample with 30, we need a sample of 80 so we could add 50 more data values to that sample to come up with our sample of 80 that's required. Anyway, the point that I'm trying to make is that we do have to have a preliminary estimate for s. The other issue is here I have this t sub alpha over 2 as my critical value, but we're not going to be able to tell what that critical value is because we're not going to know the degrees of freedom. So instead, we're going to replace that with a critical value from the standard normal distribution. So what we're really going to do is use z sub alpha over 2 times s over e squared. This formula will give us the sample size that's needed in order to be within the prescribed margin of error. We're using the standard normal distribution to find the critical value, and if you'll remember, our t distribution approaches the standard normal distribution as the degrees of freedom increase, so that's a reasonable substitution. We do have to have a preliminary estimate for the standard deviation. Let's formalize this. So determining the sample size n. The sample size n required to estimate the population mean mu with a level of confidence 1 minus alpha times 100% within a specified margin of error e is given by n equals z sub alpha over 2 times s divided by e quantity squared, where n is rounded up to the nearest whole number. So we're always going to round up to the next whole number in order to do that. And again, S is a preliminary estimate for the sample standard deviation. So now that we have this formalized, let's look at an example. A researcher wants to determine the mean number of hours per day people spend on leisure activities. A preliminary study indicates the standard deviation is 1.3 hours per day. What sample size is needed to estimate the mean number of hours per day people spend on leisure activities to be within 0.25 hours with 95% confidence? So our question is, what sample size is needed? So we're looking for n. Now, we know that a preliminary study suggests that the standard deviation is 1.3 hours, so we're given S equals 1.3 hours. And we know that we want the margin of error to be 0.25 hours because we want our estimate to be within 0.25 hours. So that's our margin of error, and our level of confidence is 95%. And so we can use that to figure out what our critical value is. Other than that, we're going to use our formula. N equals z sub alpha over 2 times S over E quantity squared. So we need to figure out what the critical value is that goes with a 95% level of confidence. So now we're using z, so we are dealing with the standard normal distribution. We need this area in the middle to be 0.95, which means the area out in the two tails will be the other 0.05. Half of that goes in each tail. Well, half of 0.05 is 0.025, so we have 0.025 in both tails. So we need to figure out what these critical values are. Well, we can do that several different ways. We can use the standard normal table. We can use inverse norm on the calculator, or we can use the normal calculator in StatCrunch to figure out what those critical values are. If I use the inverse norm command on my calculator, then I go to distribution inverse norm. 0.025 is the area in the left tail, and so that is negative 1.96, which means by symmetry this is positive 1.96, so our critical value here is 1.96. And again, we could have used our normal table to figure that out. Just quickly, if I pull in our normal table, if we're dealing with the 95% level of confidence, then the z-score there would be 1.96. And we could also use the normal calculator in StatCrunch to figure that out. So take your pick. So filling that in, I have 1.96. Again, our preliminary estimate for the standard deviation is 1.3, and the margin of error is 0.25. So I'm going to do this calculation. So if I bring my calculator back in, parenthesis 1.96 times 1.3 divided by 0.25, close the parenthesis, squared, that gives me 103.876864. So we're going to round that up to 104. And again, we always round up. We're not just following rounding procedures here. We're always going to go up to the next whole number. So the sample size required is 104. So this is the sample size required in order to estimate the mean number of hours per day that people spend on leisure activities in order to be within 0.25 hours with 95% confidence. Now, just like when we were dealing with confidence intervals for population proportions, there is no command on the calculator that's going to give us the sample size required. But there is an option in StatCrunch that we can use to give us the sample size. So let's take a look at that. So if we look at StatCrunch, to find the required sample size, we're going to go to Stat, and we have two possibilities that we could use here. We can either use this option of ZStat or we can use this option of TStat. I'm going to show you both. They work essentially the same way. First, I'm going to use ZStat because our formula is based on the standard normal distribution. Remember, we use Z sub alpha over 2 in place of T sub alpha over 2. So I'm going to go to ZStat, one sample, and we have our options for with data, with summary, and then we have our two options here for sample sizes. Well, we're going to use this bottom option, width/sample size. So I've selected that, and that brings up this window. So this window works a lot like it worked when we were dealing with proportions. I'm going to fill in the confidence level, I'm going to fill in the standard deviation, I'm going to fill in the width of the confidence interval, and StatCrunch will then tell me the required sample size. So filling in our confidence level was 95%, so 0.95 is there by default. Our standard deviation was 1.3, so I'm going to enter that. The width of the confidence interval is the difference between the lower limit and the upper limit of the confidence interval. So that's going to be 2 times the margin of error. Now our margin of error is 0.25, so 2 times that is 0.5. So I've entered in the width of the confidence interval. When I select compute, we get the sample size. StatCrunch returns the sample size of 104, which matches the sample size that we obtained when we calculated this using the formula. Now, just for the sake of showing it, if I had used the TStats option, one sample, and again, if I use the width/sample size option, I get this window. Again, I can fill in the confidence level, I can fill in the standard deviation, and I can fill in the width of the confidence interval, which again is going to be 2 times the margin of error, which in this case is 0.5. When I say compute, using the TStat option, I get a sample size of 107 instead of 104. So the reason for that slight discrepancy, which really isn't very significant, but the reason for that is because this calculator is based off of the t distribution instead of the standard normal distribution. And so in this particular case, that caused a slight little bit of variation. You can generally use either one of those options. I will typically use the ZStat option since we're using the standard normal in our formula.